Hello friends, welcome to WebTechSchool. In the earlier video, we introduced you to the data structure graph. In this video, we will look at what are the different ways we can store the graph data structure inside the computer memory. There are basically two popular ways for storing the graph inside the computer memory. The first approach is adjacency list. The next approach is adjacency matrix. Then the question comes, what actually adjacency is? Considering this given graph, adjacency is nothing but it's the list of adjacent vertices for any given vertex. So for vertex 1, its adjacency vertices are 2, 3, and 4 because we have an edge present between all these vertices. Similarly, for vertex 2, we do have an edge between vertex 2 and 1 and 2 and 4. So for vertex 2, we have 1 and 4. For vertex 3, we have 1 and 5. And for vertex 4, we have 1, 2, and 5. Similarly, for vertex 5, we have 3 and 4. So this representation, what we have just created, this has entire data for the graph. If we can store this information inside the computer memory using any of the existing data structures, then we will be able to store the graph as well. Let's look at first adjacency list. Let's say we have this graph and we have to store this graph inside the memory using the adjacency list approach. If we look back the previous representation, this data can be divided into two segments. The first segment is the list of vertices. I can say this as a key. And the second segment is basically the list of age lists or age values. So this is, I can say, a value. The data structure which can store data in a key value format is the hash table. So in adjacency list, we will use a hash table. So we have a hash table where keys are list of vertices and values are list of edges. We'll come to this. So how many vertices we have for this graph? So we have 1, 2, 3, 4, and 5. So we will create a hash table with 5 keys and let's insert all the vertices one by one. So we'll first insert 1, then 2, then 3, then 4, and then 5. For vertex 1, how many edges are present? So for vertex 1, we have 1, 2, and 3 edges. For vertex 2, we have 1 and 2 edge. Vertex 2, we have 2 edge. Similarly, for vertex 4, we have 1, 2, and 3 edge. So against each vertex, the number of data which we are storing, this can be a dynamic value. So we need to think of a data structure by which we can store values or we can grow that data structure dynamically. So the data structure which can grow dynamically is linked list. So against each key, we will create a linked list which can store these age informations. So 1 is connected to 2. So we'll against the vertex 1, we'll create a linked list with first node as 2. Then 1 is also connected to 3 in the linked list. Let's insert the node 3. Similarly, 1 is also connected to 4. So we'll insert another node 4 to the linked list. So for 1, all its edges are covered. So we'll go to next vertex. Next vertex is 2. For 2, 2 has an edge with 1 and 4. So we'll create 2 node with 1 and 4. Now let's go to 3. 3 is connected to 1 and 5. So we'll create 2 nodes, 1, and to the end of the node 1, we will add another linked list node 5. For 4, we have 3 edges. We have 1, 2, and 5. So we'll create now 3 nodes for the vertex 4. So we'll insert 1, then at the end of this node, we'll insert 2, and then at the end, we'll insert 5. For vertex 5, we have edges for vertex 3 and for vertex 4. So we will be also creating linked list for these two nodes. So vertex 3 and vertex 4. So this is nothing but the adjacency list representation of this given graph. The graph what we have described till now is an undirected graph. Let's look at for an directed graph how we can represent that graph in the same format. Okay, so this is a directed, this is not undirected. So in case of a directed graph, the idea is same. We'll use a hash table, and to the hash table keys, we will add all the vertices. So we'll add 1, 2, 3, 4, 5, all these vertices to the hash table keys. Now we'll find out the adjacency vertices. For one has only a single path to vertex 2 or a single edge to vertex 2. So we'll only add 2. Now 2 has a path to 4. So 2 does not have any other edge present. So we'll add a single node 4 to the edge list. Then for the vertex 3, we have edge to 1 and 5. So to the edge list, we will add two node 1 and 5. 1 and 5. For 4, we have a single edge present. So we'll just create a single node in the edge list linked list. Now for vertex 5, again we have a single edge present. To vertex 4, we'll add a single node. So for a directed graph and undirected graph, the representation of adjacency list is exactly same. Now let's look at how we can represent an weighted graph in terms of adjacency list. So considering this graph where we have an integer associated with every edges, how we can store this? What we have understood for storing it in adjacency list format, we need a hash table. In the hash table, we'll have key, and each key will be associated with a linked list. So a node in a linked list is actually can be represented programmatically in this manner. So where we will have a placeholder for storing data and a reference for storing the next node. If we can modify this class or struct to something like this, where it can add another property weight, then we'll be able to store an weighted graph in adjacency list format. In this case, our adjacency list will look something like this, where in the hash table, we have all the vertices, and against each vertices, we have our edge list, and inside the edge list, each node is associated with data and the weight. So one is connected to 2, so we have this, and this weight value can be 250. So this value can be 250. Similarly, 1 is connected to 3, so this value can be 170. And 1 is connected to 4, and this value can be 550. The same way, all these values we can populate. So in this approach, we can represent an weighted graph. Next, let's look at the adjacency matrix approach. Considering the given graph, what the adjacency matrix says is the same adjacency information, if we can store this in a matrix data structure or in the matrix format, that will be our adjacency matrix way. So for storing this inside a matrix, the first thing we need the size of the matrix. The size of the matrix would be equivalent to n cross n, where n is number of vertices. So for this graph, we have 5 vertices. So we'll create a 5 cross 5 matrix. So now how we can fill this matrix? So coming to the matrix, we'll see if there is an edge between vertex 1 and vertex 1. So there is no edge. So we'll fill this value 0. There is an edge between vertex 1 and vertex 2. Yes, there is an edge, so we'll fill this as 1. Then vertex 1 and 3, we have an edge, so we'll fill it as 1. Vertex 1 to vertex 4, we do have an edge, so we'll fill this value as 1. Vertex 1 and vertex 5, we don't have an edge, so we'll fill this value as 0. Coming to the next row, between vertex 2 and vertex 1, do we have an edge? Yes, so we'll fill that value as 1. Between vertex 2 and 2, there is no self loop, so we'll fill that value as 0. Between vertex 2 and vertex 3, there is no edge, so we'll fill this value as 0. Between vertex 2 and vertex 4, we have an edge, so we'll fill this value as 1. Between again vertex 2 and vertex 5, we don't have any edge, so we'll fill that value as 0. Going to the next row, between vertex 3 and vertex 1, do we have an edge? Yes, we do have an edge, so we'll fill that value as 1. Between vertex 3 and vertex 2, we don't have any edge, so we'll fill this as 0. Between vertex 3 and 3, there is no self loop, so this value as 0. Between vertex 3 and vertex 4, we don't have any edge, so we'll fill this as 0. Between vertex 3 and vertex 5, so we have an edge, so we'll fill this value as 1. Same with vertex 4 and vertex 1, we do have an edge, so we'll fill this value as 1. Then between vertex 4 and vertex 2, we do have an edge, so we'll fill this value as 1. Between vertex 4 and vertex 3, we don't have any edge, so we will fill the next value as 0. Between vertex 4 and vertex 4, we don't have any self loop, so this value will be 0. Between vertex 4 and vertex 5, we have an edge present, so we'll fill this value as 1. In the same way, for vertex 5 and vertex 1, is there an edge present? No. So this value will be 0. Between vertex 5 and vertex 2, so there is no edge, so the value will be 0. Between vertex 5 and vertex 3, so there is an edge, so this value becomes 1. Vertex 5 and vertex 4, there is an edge, so this value will become 1. Between vertex 5 and vertex 5, so there is no self loop, so this value will become 0. So this is nothing but a adjacency matrix approach. This approach we can also store for weighted graph and as well as directed graph as well. For weighted graph, instead of storing only the value as 0 and 1, we can also store the weight information in a matrix cell. Now that we have looked at both the approaches, let's look at the time complexity for doing some of the basic operation and as well as the space complexity associated with both the approaches. So on the left hand side, we have adjacency matrix, and on the right hand side, we have adjacency list representation of a given graph. So calculating the space complexity, in adjacency matrix, we need to create the matrix of n cross n size. So the space complexity would be big O of n square, where n is the number of vertices in the graph. But in a adjacency list, we need to create a hash table to store the graph. In the hash table, as part of the keys, we need to store all the vertices. So n is number of vertices in the graph. Along with that, we need to also create the linked list. And the linked list will store the number of edges present inside the graph against that vertex. So E stands for number of edges in the graph. So it will be big O of n plus E. Next is checking if there is a path present between two vertices. We can simplify this. We can say if there is a path present between two vertices. Let's say we need to find out in a given graph between 1 and 4 vertex if there is an edge present or a path present. So in adjacency matrix approach, we can straight away go to the cell location. So 1, 4th location. If the value is 1, that means there is a path present. So the time complexity for finding out if there is a path exists between two vertices or not is big O of 1 in case of adjacency matrix. But in case of adjacency list, we need to first find out the vertex. So for finding out the vertex, so as it's a hash table, so the operation would take big O of 1. Then once we get the vertex 1, against that vertex, we need to find out if the vertex 4 is present inside the linked list or not. So for finding out if a given node is present in a linked list or not, we have to traverse through the entire list in a host case. So that will become big O of number of edges in that list. So which will be equivalent to big O of E, where E stands for number of edges in the graph. So number of edges is also called as degree of vertex. So we can say big O of degree of vertex. Next operation is find all edges from a node or from a single vertex. From a single vertex, let's say from vertex 1, we need to find out all its adjacent vertices. So in the adjacency matrix approach, we can go to the row 1 and we can iterate over all these locations and find out or return back the values which has 1 in it. So in this case, we can say we do have a path present between 1 and 2, 1 and 3, 2, 1 and 3, and 1 and 4. But in case of the linked list approach or adjacency list approach, again we need to traverse through the entire list to return back all the nodes. So the time complexity would be big O of degree of a vertex or big O of number of edges for that vertex. It's recommended to use adjacency matrix for dense graphs and to use adjacency list for sparse graphs. Dense graphs are those which has large number of edges and sparse graphs are those which have small number of edges. Adjacency matrix is used where information about each and every possible edge is required for the proper working of an algorithm, like the Floyd-Warshall algorithm, where shortest path from each vertex to each other vertex is calculated if that exists. But adjacency list is a space efficient method for graph representation and can be used on top of adjacency matrix almost everywhere if the algorithm does not require it. Some of the examples are BFS, DFS, and etc. algorithm. That is all for the graph representations what I have planned. We'll be creating separate video for the implementation in both the approaches. If you have learned something today, please give your thumbs up and don't forget to subscribe to our channel. Thank you for watching.